All right, here's linear motion problem 2. For many years, the world's land speed record was held by Colonel John P. Stapp from the Air Force. He rode this rocket-propelled sled that moved on track 632 miles per hour. He and the sled brought to rest in 1.4 seconds. Can you figure the negative acceleration he experienced to slow him down and the distance he traveled during this acceleration? So for that one, we're going to go ahead and do a little kinematics calculation. Let's see. Let's see. Here's my little sketch, problem 2. Okay, we've got that rocket sled, right? That kind of rides on these rails, and it's like jet power, rocket powered, right? Got the right, shooting out to the right. We know that he is going to go from a velocity of 632 miles per hour. And eventually, at the end, the final velocity is 0, right? And we know that that's going to happen over a mere 1.4 seconds when he gets to there. You're like, man, that's a lot of velocity to lose in a very short time. So it's going to be a crazy acceleration we're going to calculate. So what I'm going to do is, like most kinematics problems, I like to list out my variables, A, V naught, V, displacement, and time. We are assuming they would like to know, we're going to assume it's a constant acceleration, okay? What we're really figuring is like the average value, right? And average means you consider it to be one constant value. What would the average be? Is what the one value that would give you the same result. So here we go. So we're trying to find that. V naught, we know, is that 632 miles per hour. Now, and the final velocity is 0. And we would like to also find the displacement, 1.4 seconds. Now I realize this is in seconds and that says hours. So right away, I know I'm going to want to do a conversion so that I get the same time units. And they say, so what I'm going to do is I could go seconds to hours, but I mean, who's going to deal with that tiny of a unit of time in hours? That's weird. I think what I'd rather do, of course, is I'd rather use the metric system. Okay, so I'm going to go ahead and metricize. Anyway, convert this. Now I could cheat and just Google, a conversion factor for going from miles per hour to meters per second, but I'm just going to go ahead and use dimensional analysis here. 632 miles per hour. You say, let's convert miles to meters. Now, the only conversion for length between imperial system of units and metric that I know, the one I have memorized, is that it's 2.54 centimeters to an inch, about. Sorry, that's the one that I know. So that means if I want to use that conversion factor, the only one that I happen to know for length, which is 600, what am I doing? The idea that 1 inch is 2.54 centimeters. Okay, that's the only metric length unit one I have memorized. So that means I got to go from miles all the way to inches, and then I can convert this from miles to centimeters. And once I'm at centimeters, I know how to go from centimeters to meters. So I can get to meters. And then the time, of course, I'm going to change from hours to seconds, and people are pretty good with that. So let's do the length one first. So I'm going to go ahead and I'm going to cancel out miles. So miles are going to go on the bottom. I know the number of feet in a mile. I know there's 5,280 feet in 1 mile. And then to go from feet, because this would give me feet, the miles would cancel. I'd have feet per hour now. To go from feet to inches, I know that in 1 foot, because I want feet to cancel, there's going to be 12 inches. So if I stopped here, I'd be at inches per hour. And I'm going to do my conversion here, use this this conversion factor that I memorized to get from imperial units to metric units. I'm going to cancel out the inches. That goes on the bottom and go to centimeters. 2.54 centimeters in an inch. And then I'll go ahead and say, hey, I know that I'm going to have 100 centimeters in 1 meter. So at this point now, I'm at meters per hour instead of miles per hour. But I want to go all the way to seconds, so I can use this time. And so now I have to convert. I'm just going to continue this on the next line. Sorry, I ran out of space here. Continuing on. So let's do the time conversion now. To do the time conversion, I want to get rid of hours. So I'm going to put hours on top to cancel this hours that's on the bottom. And I'm going to go to minutes. And I know that there's 60 minutes in 1 hour. And then likewise, let's get rid of the minutes and go to seconds. And I know there's 60 seconds in 1 minute. Okay, so when you do conversion factors, it's always that the top equals the bottom, right? This many feet equals 1 mile, this many inches equals 1 foot, this many centimeters equals 1 inch, this many meters equals, I get a meter out of 100 centimeters, right? And so on. 1 hour, 60 minutes, 1 minute, 60 seconds. So really what I'm doing, each thing that I'm multiplying by is just a form of 1. If the top equals the bottom, isn't that fraction just 1? And so I'm not changing how big this thing is. I'm just changing the units it's expressed in. That's the idea behind dimensional analysis. Anyway, when I do all this math out, crunch, 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 my calculator gives me that 632 miles per hour is 282.53 meters per second. And I know that I use this 2.54 conversion factor, which is, rounded off there. So I'm showing more digits here than I would in a final answer, right? But I'm saving some digits for the calculation to kind of reduce that rounding error. Okay, in my final answer. Okay, so anyway, so that's what the starting velocity is in meters per second. And you're just like you have a pretty good feel. 632 miles per hour is insane. So is this far. This is, holy cow. If you think about it, I mean, roughly a meter is just slightly longer than a yard, right? A meter stick and a yardstick are about the same length. So you're like, oh my gosh, that's like, I don't know, 2.5 football fields. Think about the end zones, but whatever. Anyway, point is, it's really far in a second. Anyway, so like I said, from really high speed to slowing down. And the reasons why are really interesting. If you look up Colonel Stapp, right? The video that I like to see that I like to look up in YouTube is Colonel Stapp takes a lot of G's. But anyway, point is, let's go ahead and put this in here. Find out what he was doing. He was thinking about pilots ejecting from jet fighters at high speed is what he was simulating here. Okay, so moving onward. Hey, now that I have this, hey, look, I'm trying to find acceleration. I got V naught, V, and delta x. I want to use the formula that doesn't have t. I'm sorry. I've got V naught, V, and t. I want the formula that doesn't have delta x. So that would be, yep. V is at plus V naught. Okay, and rearranging, my acceleration would be V minus V naught over t. I can put in my values, my final velocity, 0 minus 282.53 divided by a time of 1.4 seconds, right? See, now I've got the same meters per second and dividing by seconds. It'll be meters per second squared, right? And when I calculate this out, I get this incredibly fast negative 201.8 meters per second squared for my acceleration, right? And you say, hey, I would like to compare that with something, an acceleration I know. Well, what acceleration values do you know? Well, the only one you're likely familiar with is 9.8 meters per second squared, because that's g. And so if I divide that out, right, divide by 9.8, I'm going to get that this is 20.6 g's. So if my acceleration is 20.6 g's, that what I'm saying here is this acceleration, there's a force needed to make something accelerate this, right? It would be its mass times this acceleration. And you say, well, mass times 1g is how heavy you are, right? How hard gravity pulls on you. So I need a force more than 20 times this guy's weight to stop him. I mean, this guy's getting smushed in his seat. This is a very dangerous, very high acceleration. The force needed to give you that acceleration is really big. And if you watch that video, you'll see the effects that had on him. But anyway, so that's that first part. Now, they did want to know how far he went. So how far it took to stop him. So if I want to do that calculation, well, now I have an acceleration. That's going to make this a lot easier. I have all my motion variables now except delta x. So I could use my choice of formulas with displacement in them. Just for the heck of it, I'm going to choose to do, we'll do this one. It already has the delta x isolated. So delta x is v naught t plus 1/2 at squared. And so my displacement is going to be that 282.53 times 1.4 seconds plus 1/2 negative 201.8 times 1.4 squared. And so if I plug that in my calculator, right, I'll get a displacement. Let's see, 282.53 times 1.4 minus 0.5 times 201.8 times 1.4 squared. And I get 197.8 meters needed to stop him. So, I mean, he stopped over 2 football fields length. Alrighty, very roughly. Okay, that's it for that problem. Bottom line, typically from this is be careful with your units, okay? If I'm going to be combining these, I'd really want to have the same time units. And it makes sense to get something you can think about. Comparing it to G is a good idea. So converting to meters, my miles. Okay.